Let us understand the concept of Costas loop with the help of fundamentals. Recall that when a BPSK modulated signal gets rotated by a phase offset, the amplitude is reduced. This is because after the rotation, the actual amplitude is given by the projection on this axis, which is given by cos of this phase offset. Similarly, we have a Q component, which is not used for detection purpose but for synchronization purpose only, and this naturally is given by sine of theta delta. In the feedback setting, we do not use theta delta, we use theta delta E, where E signifies that the error is being continuously updated. The phase error is being continuously updated. So from here we can see that after the down conversion and low pass filtering, the I part is given by the incoming signal, which only contained an in phase component, cos of theta delta E, and the Q component is given by VIT sine theta delta E. We ignore the negative sign here because this just comes up because of the way in which we constructed the transmitted signal. Now imagine that this theta delta is very close to 0 to understand its operation. So here we can see that we are taking the sine of ZIT. Why? Because when this is very close to 0, this value almost equal to the data symbol in the I arm. And in BPSK modulation, there is only one data symbol in the I arm and no data symbol in the Q arm. So when this is very close to 0 theta, then this value is close to the actual symbol. And we can say that if we take the sine of this output, we get an estimate of our data symbol. What we do next is that when we multiply this with the output from the Q arm, we get Vi square T and cos theta delta E sin theta delta E. Using a trigonometric identity, we get sin 2 theta delta E. Now remember that this is very close to the actual data symbol, which was +1 or -1. With the squaring, this is gone. If theta delta is very close to 0, then we can use the approximation sin theta is nearly equal to theta, and this 2 cancels out with this 2, and the result is that our error signal is very close to the actual phase error between the transmitter and receiver local oscillators. Costas loop in QPSK modulation case looks a little bit complicated, but actually it is easier than what we encountered in the BPSK case, and its principle of operation is very interesting. Assume again that the phase offset theta delta E is very close to 0. In that case, the output in the I arm is very close to our data symbol in I arm, and the output in Q arm is very close to our data symbol in Q arm. And we can say that sin ZIT is nearly equal to A hat IM and sin ZQT is equal to A hat QM. When you multiply this with ZQT and this with A hat Q and subtract them, look what we got. Sin ZQT ZIT minus sin ZIT ZQT, and this is A hat Q ZI minus A hat ZQT. Compare this expression with the cross product phase error detector. And you can see that other than a difference of a negative sign, this is very similar to a cross product phase error detector. And hence we can say that the Costas loop is an approximation of the maximum correlation or maximum likelihood methodology. And this is what made Costas loop so attractive, because in a system like a squaring loop, the RF components had to work on double the frequency. In Costas loop, the circuit operations are being implemented at carrier frequency. Let us take an example of GNU radio block, which is called the Costas loop block. It has 3 parameters. Loop bandwidth is the equivalent noise bandwidth we covered in the context of a PLL. The order is a modulation order, which is 2 for BPSK, 4 for QPSK. Use SNR points towards a more accurate phase estimation method, where we include the noise variance, which makes the estimate more accurate. So in this example, we have the loop bandwidth of 2 power 100 QPSK modulation. So order is 4 and a CFO of minus 0.043. Not a phase offset, but a CFO. And here we can see that the input constellation is rotating. They are rotating in a circle. And after convergence, we can clearly mark these 4 separate points. There are two things I want to mention here. One is that a PLL and a Costas loop, because they are tracking a slowly varying phase offset, they can track a frequency offset as well if it is small enough. Secondly, the final lock point is rotated because we chose a CFO such that it is at the edge of the lock range.
Let us discuss the implementation of Costas loop in GNU Radio now. We have a sample rate of 32,000 here with the samples per symbol as 4. The phase offset, frequency offset, and the loop bandwidth are defined through sliders in which the phase offset goes from minus pi to pi. The frequency offset goes from minus sample rate over 2 to sample rate over 2. So from minus 16 kilohertz to 16 kilohertz. And the loop bandwidth is defined as the default value is 2 pi over 100, which is the usual case, and we can take it to 1. Excess bandwidth is zero point 0.5, and we have defined a tab widget which switches between phase and frequency, which we will shortly see. The flow graph starts with bits generation and the throttle block. This is a custom QAM block which is discussed in the previous lecture as well. And here comes the interesting part. There is a mistake I have done here. This should have been a meshed filter. I have included a signal source here with which the waveform is being multiplied. Why? Because I want to introduce a frequency offset as well as in addition to the phase offset. Remember that in the previous flow graph, we just multiplied with a complex constant e raised to power j theta. Right now, I'm introducing the phase offset through the initial phase of the complex sinusoid and the frequency offset through the frequency offset of the complex sinusoid. The data type is complex, so it's e raised to power j omega t plus theta, if we can say that. This e raised to power j omega t plus theta is multiplied with the QAM baseband waveform to introduce both a frequency error and a phase error. Initially, we will keep the frequency error to 0 to see the convergence for the phase error, and then we will switch to the frequency offset as well. After the match filter, we downsample it by samples per symbol, which means we discard samples per symbol, which is 4 minus 1 equals 3 values. 3 samples in every 4 samples, and pass the sample corresponding to the symbol estimate to the Costas loop block. Costas loop block has a minimal set of arguments. It's a loop bandwidth. We have already defined it here, and the order is 4 due to this being a 4 QAM or QPSK modulation. SNR, yes or no, we can say it as a yes for an optimal implementation. Let's run the flow graph and observe the output. This is the tab between phase and frequency, and right now we'll focus on the phase offset. So this is the input to the filter. After filtering and downsampling, we have a perfect constellation, and the Costas loop output is sort of similar to what should have been. These are the frequency, phase, and the error signal. These are all output of the Costas loop block for as a monitor. Let us change the phase offset now and see the convergence process. As we do that, the constellation starts rotating both before and after the filter. However, we see that the Costas loop actually locks onto, since it is already locked on to the input phase, it's producing a proper constellation output. The phase offset here has changed. The error signal is still being generated, and the frequency error is 0. Here you can see that the phase offset is 0.6 and the phase offset is zero point 0.6. These are the automatic outputs from the Costas loop block. And now we can play around with these values and see the convergence process. Even if for large swings, the output is reasonably stable. As far as the loop bandwidth is concerned, a larger loop bandwidth results in a quicker acquisition time but a higher steady state error, while a lower loop bandwidth results in slower convergence but a lower steady state error. Since the relationship between the loop bandwidth and the settling time or the final steady state error is not linear, a general rule of thumb is that we start with some prescribed value. Just for example, 2 pi over 100 was chosen, and then adjust this according to the realistic model parameters such that a desired quality metric, for example, an error vector magnitude, is satisfied. Error vector magnitude basically takes a Euclidean distance between the ideal constellation point and the receiver constellation. Let us switch to the frequency tab and see the effect of frequency offset. As we know that the rate of change of phase is known as frequency, once we introduce a frequency offset, the constellation would be rotating both before the filter and after the filter, and the Costas loop is able to recover this small frequency offset. That's why we see there is a slope with the phase as well. This green line is the error signal and blue line is the frequency offset estimate. We can increase the frequency offset slowly and see the hold range, how long the acquisition is sustained. And the purpose of these tabs is to play with the parameters and see where the system can be broken. While it could not lock onto the signal for the frequency offset of 1400 Hz, after increasing the loop bandwidth, you can see that the Costas loop has been able to track that frequency offset as well. For a very large frequency offset, much of the signal energy has been filtered out and it has not been able to recover the signal now. Here we can see that we can at least mark distinct 4 regions for the 4 constellation points. And so we can play with the system in the same manner. The frequency offset in this case is minus 1000 Hz. In fact, the frequency offset is available here. This value is minus point, close to minus pi by 4. Let us go back to the flow graph now and see that the sample rate is 32,000. So 1000 over 32,000 is 1 over 32. And after the downsampling by samples per symbol, which is 4, it's 4 by 32, which is 1 by 8. When you multiply it with 2 pi, it becomes pi by 4. And that was the value displayed by the frequency offset estimate.
The original Costas loop concept was not based on a match filter. It was actually based on a low pass filter. So let us disable the match filter and enable the low pass filter and check the output of the phase recovery loop. When that is done, you can see that because the low pass filter is not matched to the incoming waveform that was shaped by a pulse shaping filter, a root raised cosine filter, we have intersymbol interference in the receive signal. And once we introduce a phase offset, the Costas loop can still compensate for the phase error.
The point I want to explain is that the original Costas loop proposed by Costas himself was based on the low pass filter, and it still works with the low pass filter as well. One final question we have here is that why can't we build a Costas loop from our own custom blocks in GNU Radio Companion instead of using a built-in block like this one? The answer, as we found earlier in the case of phase lock loops, is that we can't perform loops in the flow graph because of the way the data moves between different blocks. What really happens is this is from GNU Radio website. What really happens is a block is passed a large chunk of data from the previous block. A loop could be implemented if it was a sample by sample passing operation. However, as I mentioned here, we can still do loops in GNU Radio, not just in GNU Radio Companion. For example, I can show you the Costas loop code on the website, and you can see here that once you break through these programming barriers, you can see that the phase detector is simply implemented through the same equation we mentioned in the lecture. So basically we are taking the sign of the I arm, here we are taking the sign of the Q arm and multiplying this with the imaginary part and this with the real part. Taking the difference is just a simple phase error detector we have discussed in the equation. Similarly, for a BPSK Costas loop, we just multiply the real and the imaginary parts together. There is also an implementation for an 8PSK, which you can explore in detail later. The point I am making here is that you can easily build your own custom algorithms by taking these blocks as the initial framework and then changing them as necessary.
The small picture of carrier phase synchronization is that after timing and carrier frequency recovery, the match filter output is downsampled to one sample per symbol. Modulation is removed through a product with the data symbol conjugate, and the underlying waveform is just a simple constant complex number, the phase of which is the desired carrier phase offset.